Have you ever seen this symbol in a math class and thought, oh no, what is that? Well, today we are going to pull back the curtain on the Greek letter sigma. And trust me, by the end of this, you'll see it's not some scary monster, but actually one of the most powerful and honestly elegant tools in all of mathematics. So let's get into it. Okay, let's start with a little thought experiment. Imagine I asked you to write down how to add up all the even numbers starting at 2 and going all the way to 100. You'd start writing, 2 plus 4 plus 6 plus 8, and you'd just keep going. It's long, it's messy, and it's super easy to mess up somewhere along the way. There's got to be a better way, right? Of course there is. And this is it. This is sigma. In the world of math, it's basically a super compact way of saying, hey, add up a whole bunch of things that follow a clear pattern. Think of it like a piece of code. It's a shorthand that lets us express that crazy long sum of numbers in just one neat little symbol. So to actually use it, we have to break it down and see what makes it tick. It's kind of like learning the grammar of a new language. Once you know the basic parts and what they do, you can start reading and writing with it no problem. First up, we have the index. You'll usually see it written as a little I or a K or maybe an N. This little guy is the workhorse of the whole operation. It's basically a counter that ticks up by 1 with every single step of the process. If you've ever done any programming, it's just like a counter in a loop. So how does that little counter know when to start and when to stop? Well, that's where the limits come in. The number below the sigma is your lower limit. That's the starting number for your counter. And the number on top, that's your upper limit, which tells the counter, okay, you're done. They're literally the start and stop buttons for your sum. And finally, there's the expression right next to the sigma. This is the rule. This is the actual math you have to do at every step. As your counter ticks up from the start to the stop, you plug its value into this formula. This is the what to do part of the whole instruction set. Okay, so let's put it all together in one spot. The sigma symbol itself tells you to sum stuff up. The index, your I or K, is the counter. The limits give you your starting and ending points, and the formula to the side is the rule you have to follow. The whole thing is like a complete self-contained instruction manual for doing math. All right, that's enough theory. Let's be real. The best way to get a feel for this is to actually see it in action. So let's translate some of this math code into actual numbers. Let's check this one out. The notation tells us we need to sum up k squared. Our counter, k, starts at 1 and it's going to stop when it hits 4. Simple enough. So we start with k equals 1 and we square it. That's 1. Then we plug in 2 and square it. That's 4. Then 3 squared is 9 and 4 squared is 16. Finally, we just add up all those results. 1 plus 4 plus 9 plus 16 gives us a grand total of 30. See? Not so bad when you break it down. But here's where sigma notation really starts to flex its muscles, with huge sums. Take the classic problem of adding up all the numbers from 1 to 100. You could do it the brute force way, but why would you? There's a well-known formula for this exact situation, famously figured out by the mathematician Gauss when he was just a kid. And it perfectly shows just how efficient this can be. By using that simple formula where n is just our upper limit, 100, the calculation becomes a piece of cake. 100 times 101 divided by 2, and you get the answer in seconds, 5,050. No adding 100 different numbers, just one elegant, quick calculation. That is the power we're talking about. Now, as powerful as this is, it's not foolproof. There are a few common mistakes that trip people up when they're first learning. So let's go over them real quick so you can steer clear. Okay, number 1, be really careful with your counting. A sum from 1 to 5 has 5 terms. That's easy. But a sum from 0 to 5 actually has 6 terms. It's a classic off by 1 error. Second, make sure your index variable, your k, is actually in the formula you're summing. If it's not, you're just adding a constant over and over. Which brings us to number 3. If you are summing a constant, say the number 7 4 times, the answer isn't 7. It's 7 times 4, which is 28. So you might be thinking, okay, cool, but is this just some neat trick for my math class? Absolutely not. Learning this notation is like getting a key that unlocks a whole bunch of bigger ideas in science, tech, you name it. Getting comfortable with sigma is going to be a huge help down the road. It is literally the language of series and calculus. It's absolutely essential for probability and statistics. And like we said, it's the core idea behind loops in computer programming. You're going to see this everywhere. And here is a perfect real-world example from statistics. This is the formula for expected value. It might look a little intense at first, but now we can decode it, right? It's just telling us to sum up every possible outcome, x, multiplied by the probability of that outcome, p of x. This is used all the time in finance, insurance, and so much more. So here's the big takeaway. Sigma isn't just a shortcut for addition. It's a powerful way to package up a really complex, repetitive process into one clean, elegant expression. It's a language for describing patterns in the world around us. So we figured out how to add a set number of things, whether it's 4 terms or 100 or 1,000,000. But that begs a pretty wild question. What if that number on top of the sigma wasn't a number at all? What if it was infinity? What happens when you try to add up an infinite number of things? Just think about that for a second, because that's the doorway to calculus.